Okay, so now we know the definition of a topology and examples of different topologies. Um, Now we would like to talk about the meaning of a basis for a topology. Now, why the question is, why do we need a basis if we can list all the subsets? Now, a topology can be something really large. So if you take the set of real numbers, and if you take, for example, a finite complement topology, we are not able to write all the sets of the topology. So a basis gives us some kind of an easy way to generate the topology. So we will define a basis, and this basis is different from a basis, for example, a basis of a vector space. So the definition is that, so we have a topological space, so I'll take let x t to be a topological space. A basis, so usually we write a script B. Oh, in the notes you should see a capital B. For T is a subcollection. Is a subcollection of T with the property that each member of the topology is a union of members of B. So basically what this is saying, if I can write any, so I have a set, say a set A in the topology. This implies that A is the union of some members of Bi, where Bi belongs to B. Not all the members, so it should be some members. So if you can write any member of the topology as some union of members of B, then we say that B is a basis. And also it's important to note that sometimes we forget about the topology and just say that B is a basis for X. We refer to B a basis for X instead of T. So that is something that we use occasionally in topology. We're talking about a basis for the topology, but we just talk about the basis for the space. And we call members of B, or the basis, are called basic open sets. And we call T the topology generated by B. Okay, so we look at a couple of examples. So I will take the first example that we did. where we had A, B, C, D, E, F as my set X, and T1 with X, the empty set, A, C, D, A, C, D, and B, C, D, E, F. And now we want to take a basis. So and it is important that the basis should be smaller than the topology itself, otherwise it's kind of useless. So in this case I can take the set A and set CD, and the set B, C, D, E, F will be a basis for X, because if I can take the union, I can write any member of T as the union of members of B. Now we don't have to write the empty set as the union of the members of B, so that's kind of trivial. So we should be able to write the non-empty sets of T as members of B. Now the second example will take X to be any set, and if I take the collection of singleton subsets of X, then this is going to be a basis for the discrete topology. Discrete topology contains all the subsets or the power set of X. So I can generate any set by using the singleton sets, because I can write any set as the union of singleton sets. So this is a basis for the discrete topology.